In this video, we're going to learn about the three-dimensional coordinate system, how it compares to the two-dimensional coordinate system, the similarities and the differences, and we'll also look at extending some mathematical ideas from 2 dimensions into 3, and what that entails. Now, thinking in 3 dimensions can be challenging. Most of the work you've done up to this point has been in 2 dimensions, so we've been able to do it on a piece of paper. We can graph, manipulate, and get a good understanding of what we're working with. Now, in 3 dimensions, we're still going to work on that piece of paper, but we're missing a dimension. So one tool that can help in this area is visualization, using the space around you to help you understand what we're talking about in 3 dimensions. We live daily in a 3-dimensional environment, so use the classroom or the room you're in to represent different parts of the 3-dimensional coordinate system. So the floor, the walls, the ceiling, where they all intersect. That will be a great way to help you visualize the 3-dimensional coordinate system, so then when you go back to the piece of paper, it will start to make sense. Now, it's not going to be easy, it's going to take some time, but before we get to that part, let's start with the basics. The set of all ordered triple pairs of real numbers x, y, z defines 3 space and is denoted as R3. So, our points x, y, z, nice extension from the points in 2 space, x, y. R3 is our formal notation of 3 dimensions or 3 space. Those words are interchangeable. So 2 space or 2 dimensions would be R2. Now looking at the coordinate systems, the 3D coordinate system adds a z-axis to the 2D coordinate system. So we're familiar with the 2-dimensional coordinate system. We have an x-axis and we have a y-axis. So intuitively, it would seem that this new axis coming out of the page should be the z-axis, right? Where the horizontal stays the x and the vertical stays the y. But our standard orientation in 3 space is actually going to be a bit different. The axis coming out of the page is going to be the x-axis, the horizontal will be the y, and the vertical will be the z. There are a few reasons for this. One that makes sense to me is in 2 space, x typically represented the inputs, y represented the outputs. So we had the outputs on the vertical axes. In 3 dimensions, z is going to represent our outputs, and x and y's are going to represent the inputs. So we still have our outputs on our vertical axes, and now our inputs, because there will be 2 of them, is the plane that is horizontal, just like the x-axis was the horizontal axis. As far as y, x is coming out and y is horizontal, we still want the orientation of the xy plane to stay the way it does. So positive x, then positive y, and then we go to negative x and negative y. And for completeness, we can put the negative z-axis in there. Okay? And all the rotations, angles, all of that stays the same if we orient the axes x, y, z. Now, the 3 coordinate axes determine 3 coordinate planes. So the 3 coordinate planes are the planes that contain 2 axes at a time. So the xy plane is the plane that contains the x and the y axes. That's our xy plane. And any point on this plane, z will be 0. And then we have the yz plane. So that's the one right there, containing the y and the z axes. And every point there will have an x value of 0. And then the last coordinate plane is the xz plane. So that contains the x and the z. So that's our xz plane. Now, those 3 coordinate planes divide 3 space into 8 different sections. So we call them octants. In 2 space, we had quadrants, right? Quadrant 1, 2, 3, 4. So in 3 space, we'll have octants, and there'll be 8 of them. And the one we focus on the most is the first octant, which is where x, y, and z are all positive. So another benefit of the way that we orient the axes in 3 space is the first octant is the one that we see the best, right? Visualized right there in front of us. And that's really the only one we will refer to. Unlike 2 space, where we cared about all the quadrants, really we'll only focus on the first octant when we are naming octants in 3 space. Okay? There are a few other reasons why the orientation goes x, y, z based on some of the operations that we'll learn in the coming videos. Okay, so scrolling down, those are all the pieces that I just spoke about. Now, plotting points in 3 dimensions is more art than a precise science. In 2 space, it was precise, right? You had to plot a point exactly where it belonged. In 3 space, it's more about the reasoning of getting to the point than where the actual point is. So for instance, if we want to plot the point letter A, 3, 1, 2, so we have an x, a y, and a z. Right, so we'll label our axes to get used to the orientation. We'll put some tick marks on our axes, so evenly space them out. I'll put 3 on each. Okay, so 3 on the x, so we're going to start at the origin, so we go 3 along the x, then 1 on the y. So we can create this parallelogram here on the xy plane, and then we're going to go up 2 on the z. So what we can do is we could take this parallelogram and translate it up 2 off of the xy plane. It's a little congested, but hopefully you can kind of get a sense of that rectangular prism there. So the point 3, 1, 2 is going to be the point, the vertex of the prism opposite the origin, on the diagonal of the origin, I should say. Okay, so that is our point A. So if I label the sides of the prism, right, 3, that's our x, 1, that's our y, and then 2, that's our z. So each coordinate really is telling us the distance from one of the coordinate planes, right? So this point is 3 away from the yz plane. It's 1 away from the xz plane, and it's 2 away from the xy plane, right? So that thought process is really what we're concerned more about than where you actually put the point. So then for point B, 2, -3, 2, we'll start the same way. Let's label our axes, x, y, z. In this case, our coordinate has some negative components. So we need the negative y-axis, and we also need the negative z-axis. So same thing, let's start evenly spaced marks along the axes we're going to focus on. And then we go through the same process. So 2 along the x, now -3, so we go along the y-axis. We create that parallelogram on the xy plane. And then we're going down 2 on the z-axis, so we can translate that parallelogram down. And now we have our prism, and the point B is the point on the diagonal across from the origin. So this point right here would be point B. The same thing, we can label the sides, but that thought process and being able to think in 3 spaces is what's most important here in this exercise. Okay, so now that we have points in the coordinate system defined, let's talk distance, right? Distance between points more particularly. So if we recall, the distance between points x1, y1 and x2, y2 in 2 space is the square root of x2 minus x1 squared plus y2 minus y1 squared. Right? That's the distance formula. It comes from the Pythagorean theorem, something we're all familiar with. So now to extend that into 3 dimensions, we're just going to add a z component to it. So the distance now between points x1, y1, z1 and x2, y2, z2 is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And again, that comes from the Pythagorean theorem, a couple of Pythagorean theorems in this case, and we put them together and we get the distance formula in 3 space. So difference of the x's squared, difference of the y squared, and now the addition of the difference of the z's squared. Okay, so now let's find a few distances. So find the distance from the point 4, -2, 3 to first the xz plane. So this is more like plotting the point, right? Thinking in that term. So the distance from the xz plane, one of the 3 coordinate planes, is going to be how far along the y-axis we went. So to plot this point, we would go 2 along the negative y-axis. So we're going to be a distance of 2 away from the xz plane. So the distance we're looking for is 2. Now the distance to the origin. So the origin is the point 0, 0, 0. So we're going to use the distance formula between the point 4, negative 2, 3 and the point 0, 0, 0. So square root of 4 minus 0 squared plus negative 2 minus 0 squared plus 3 minus 0 squared. So simplifying, we have 4 squared, so 16, negative 2 squared, so that's 4, and 3 squared, that's 9. So the square root of 29 is the distance we're looking for. Now we want to find the distance from the point 4, negative 2, 3 to the z-axis. So that's a little bit more challenging. We need to think about a point on the z-axis that we can use the distance formula for. So the closest point on the z-axis to the point 4, negative 2, 3, so remember the z-axis is above the origin, so the x and the y would both be 0, and then the z value to place the point closest to 4, negative 2, 3 would be the same z value, so in this case 3. So the point 0, 0, 3 will be the closest point to the point 4, negative 2, 3 on the z-axis. Right? And think about that. Takes a second to make sense there. And then we're going to use the distance formula again. So square root of 4 minus 0 squared plus negative 2 minus 0 squared plus 3 minus 3 squared. Okay, so square root of 4 squared is 16, negative 2 squared is 4, and then 0 squared would be 0. So square root of 20. If we wanted to simplify that, square root of 4, square root of 5, 2 square root of 5. Okay, now would be a good opportunity for you to pause the video and try letter D on your own. Find the distance from the point 4, negative 2, 3 to negative 1, 3, negative 5 by yourself. Once you're done, play the video and see how you did. Okay, so grabbed a different color here. So we have the square root of 4 minus negative 1 squared, so that turns into plus negative 2 minus 3 squared, plus 3 minus negative 5 squared. Also turns into addition. So we have 5 squared, so 25. Negative 5 squared will also be 25. 8 squared will be 64. So the square root of 114. Perfect. Hopefully that's what you got in your own work. Now, naturally building from the distance formula would be the equation of a sphere. In 2 space, that would be the equation of a circle. So for a sphere with radius r and center HKL, the equation will be x minus h squared plus y minus k squared plus z minus l squared equals r squared. All right, so if we remember a circle in 2 space, x minus h squared plus y minus k squared equals r squared. So we're adding in that z component to now turn the equation from a circle to a sphere. Still have the center, HKL, right? And we're still squaring our radius. So find the equation of the sphere with center at 0, 5, negative 3 with a diameter of 14. Another great moment to pause the video, try this on your own, and then play to see how you did. Okay, so hopefully you noticed if they gave you the diameter, the first thing you need is the radius. So in this case, that would be 7. So we can start to build our equations. So x minus 0 squared plus y minus 5 squared plus z plus 3 squared equals 7 squared. We don't need the x minus 0, but just for completeness here. And then we can simplify that to be x squared plus y minus 5 squared plus z plus 3 squared equals 49. And there we have the equation of the sphere, centered at 0, 5, negative 3, with a diameter of 14 and a radius of 7. Now, coming along with the equation of a sphere or a circle oftentimes is completing the square. So in this case, they want us to show that the equation x squared plus y squared plus z squared minus 6x plus 8y plus 2z plus 15 equals 0 is the equation of a sphere and find its center and radius. So some of you are probably thinking to yourself, oh, perfect, I know how to complete the square. And then others are a little hesitant, going, I'm not sure if I remember how to do it. Either way is fine. Let's go through this together. So let's rearrange the equation. So x squared minus 6x plus the value for the x's to complete the square, plus y squared plus 8y plus the value for the y's, plus z squared plus 2z plus the value for the z's. We'll move the 15 over, so negative 15. And then we'll add those three values from the left side to the right. So complete the square. Half of the middle term, so negative 6 would be negative 3 squared is 9. Add 9 on the other side. Half of 8 is 4, squared 16. We'll add that over here. And then half of 2 is 1, squared is 1. Add that. So we factor, so x minus 3 squared plus y plus 4 squared plus z plus 1 squared equals 11. So that means our center is the point 3, negative 4, negative 1, and the radius is the square root of 11. Okay, so we've talked about points, the coordinate system, plotted points, distance, and we built from distance into spheres. So the last part of the video, I want to look at a few equations that we're familiar with in 2 dimensions and see how they extend into 3. So the first one, y equals x. So let's label our axes, both 2 and 3 space. Okay, so in 2 space, y equals x is a line. So let's see if I can use the line tool here. Get an arrow on both ends. Not sure where the arrow went, but that's okay. I'll put it in myself. Oh, still have the line tool. Get rid of that. Go back to the marker. There's our arrow. Okay, so we have a line in 2 dimensions. So now in 3 dimensions, notice that there's no z in the equation. So we have to figure out what that means for our graph. So this line would still stay there in the xy plane. But now, since z is not in the equation, z can be anything. Right now I drew z equals 0. So z could be 1, and there we have that line. Z could be 2, and we'd have that line. Or z could be negative 1, we could be below the xy plane. So we'd have all of these lines, an infinite number of them, all stacked together. And if we take all of those lines together, and I'll grab red, and we draw, we're going to have a plane. So a line in 2 space is going to extend into 3 space as a plane. Let's look at a few more. So x plus z equals 1. So we label x, y, z. Okay, so this is a line in 2 dimensions. Right, in the xz plane, if I drew out the xz plane, this would be the line where both of these intercepts are 1. Right, so 1, 1, there would be our line. But now y can be anything. So that's y equals 0, or y could be 1, or y could be 2, or y could be negative 1. We have all of these infinite number of lines stacked together. And again, if we group them all together, okay, we're going to have a plane. Now remember, this plane does extend infinitely in both directions, right? We're representing it with a parallelogram in this case, but it does extend infinitely. So then we have x squared plus y squared equals 4. So in the xy plane, in 2 dimensions, we know this to be a circle of radius 2. But now in 3 space, so we have our x, we have our y, we have our z. The equation has no z in it. So 1, 2, 1, 2. So we have a circle of radius 2 in the xy plane. But that's where z equals 0. But remember, z could be anything. Z could be 1, so we'd have a circle up here. Z could be 2, so we'd have a circle up here. Z could be -1, so we'd have a circle down there. We'd have a stack of all of these circles, an infinite number of them. And when we group them all together, it's going to create a cylinder. Right? So that circle in 2 space now extends to 3 space as a cylinder. So the last example I want to look at is with an inequality. Right? What changes when we have an inequality now? So if we simply had x squared plus y squared plus z squared equals 9, we would say sphere of radius 3 centered at the origin. And that would be a perfect description of the region. Right? So the equals, that tells us we have all the points on the sphere. But what does the greater than say? Remember, we're trying to describe a region. Now we have an inequality greater than. So that means that we can have points that are outside of the sphere. Right? So these are going to be outside of the sphere. So if we want to best describe this region, it's going to be the set of all points on or outside the sphere of radius 3 centered at the origin. So, a lot of different pieces in this video, from the coordinate system to distance to spheres to extending equations. Some of it might have made sense the first time, some we're going to have to work at, and that's okay. Right? Thinking in 3 space is new, so don't let it frustrate you. Just keep working, keep working, keep working, and I promise you it will start to make more sense as it goes along.